Hello, welcome to StatTrek's video tutorial on Advanced Placement Statistics. This lesson covers measures of central tendency. Sometimes, statisticians use a single number to describe the most typical value in a set of numbers. For example, there are hundreds of colleges in the United States, most with different tuition. Even so, we can describe the tuition at a typical college by saying the average college tuition is $10,000. This kind of number is called a measure of central tendency. The two most common measures of central tendency are the mean and the median. By the end of this lesson, you will be able to compute a mean and median, explain the advantages and disadvantages of each, and describe what happens to the mean and median after adding a constant to every value in the dataset or after multiplying every value in the dataset by a constant. Let's talk about how to find the mean. Calculating the mean of a set of values is a two-step process. First, find the sum of all values. Second, divide the sum by the total number of values in the group. This two-step process is expressed by a simple formula. The mean is equal to the sum of all values divided by the number of values. Statisticians use special notation to express the formula for the mean. And that notation differs slightly depending on whether you're talking about a population mean or a sample mean. For the population mean, notation begins with the Greek letter sigma, which means to compute the sum of whatever follows sigma. Thus, sigma x means to sum the values of variable x for every observation in the population. The capital letter N represents the number of x values in the population, and the lowercase Greek letter mu represents the population mean. Using this notation, we can express the formula for the mean of the population as follows. This formula simply says that the population mean is equal to the sum of all population values divided by the number of population values. Notation for the sample mean uses the same uppercase sigma for summation. After that, things are similar but not exactly the same. The sum of all x values is denoted by sigma x, where x is lowercase. And the number of x values is denoted by a lowercase n instead of an uppercase n. And the sample mean is denoted by x bar instead of mu. So the formula for the sample mean looks like this. These formulas illustrate a common theme with statistical notation. Population attributes are often denoted by Greek letters or uppercase Roman letters, and sample attributes by lowercase Roman letters. Let's apply the formula for the mean to some data. Suppose we want to compute a mean bowling score, giving the scores shown in the table. We begin with the formula for the mean score. The mean is equal to the sum of bowling scores divided by the number of scores. The sum of scores is equal to 100 plus 170 plus 130 plus 140, which equals 540. The number of scores is equal to 4. Plugging these numbers into the formula, we see that the mean bowling score is equal to 540 divided by 4, which is 135. The other measure of central tendency that we want to look at is the median. So let's talk about how to find the median. The median is the midpoint in a set of data. To find the median, list all the scores in order from smallest to largest. If there's an odd number of scores, the median is the middle score. If there's an even number of scores, the median is the sum of the middle two scores divided by 2. Whether you begin with an odd number of scores or an even number of scores, the median is always the middle score. It always has the same number of scores above it as below it. Let's find the median score from a set of 5 bowling scores. Step 1 is list the scores in order from smallest to largest. Then, with an odd number of scores, identify the middle score. And we see that the median bowling score, shown in red, is 140. Suppose we had an even number of scores. Step 1 is the same. List the scores in order from smallest to largest. Then, with an even number of scores, identify the two middle scores, which are 130 and 140. The median is the sum of the middle two scores divided by 2. So the median is equal to 130 plus 140 divided by 2, which is 135. So, which is a better measure of central tendency, the mean or the median? It may depend on whether the data set includes outliers. An outlier is an extreme value that differs greatly from other values in a data set. Generally, the median is a better measure of central tendency if you're dealing with a small set of scores that includes an outlier. The mean is better if you have a large set of scores without an outlier. Suppose you wanted to describe the household income of 5 families with a single number. Let's say the first family earns $60,000. The second family earns $70,000. The third family, $80,000. And the fourth family, $90,000. But the fifth family earns $10 million. Let's find the mean and median to see which would be the best measure of central tendency for these families. Remember that the mean is equal to the sum of incomes divided by the number of incomes. So we can compute the mean as 60,000 plus 70,000 plus 80,000 plus 90,000 plus 10 million, all divided by 5, which equals 2,060,000. What about the median? The median is the central value in an ordered list of values, which in this case is $80,000. Do you think the mean or the median is a better measure of typical household income? At over $2 million, the mean greatly overestimates income for 4 of the families and greatly underestimates income for the outlier. Whereas the median, at $80,000, is fairly close to the income for 4 families and only badly underestimates the income for the outlier. So in this example, it looks like the median is a better indicator of typical household income. This example illustrates the point we made earlier. When you have a small sample with an outlier, the median is often the better measure of central tendency. If you plan on taking the Advanced Placement Statistics exam, you will be expected to know what happens to the mean and the median when you add a constant to every element in the data set. So what does happen to the mean and median when you add a constant to every value in the original data set? Answer: the mean and median increase by the same constant. Let's work through an example to illustrate this point. In this example, the original data set consists of 5 values, 0, 2, 4, 4, and 5. To compute the mean, we need to compute sigma x, the sum of all values in the data set. Sigma x is 0 plus 2 plus 4 plus 4 plus 5, which equals 15. We also need to know the number of observations in the data set, which, in this case, is 5. With that info, we can compute the mean, which is sigma x divided by n, or 15 divided by 5, which equals 3. We also want to find the median. The median is the middle value in an ordered set of values. In this example, the middle value is 4. So the median is equal to 4. Now, let's see what happens to the mean and median after we add the constant 10 to each value in the original data set. Adding 10 results in a new data set with entries of 10, 12, 14, 14, and 15. To compute the mean of the new data set, we need to compute sigma x, the sum of all the values in the data set. Sigma x is 10 plus 12 plus 14 plus 14 plus 15, which equals 65. The new data set still has 5 values, so n is equal to 5. Given sigma x and n, we can compute the mean of the new data set, which is 65 divided by 5, or 13. And finally, we observe that the median of the new data set is its middle value, which is 14. So what happens to the mean and median after we added a constant, 10, to each element in the original data set? The new mean is 13, which is equal to the old mean, 3, plus the constant, 10. And the new median is 14, which is equal to the old median, 4, plus the constant, 10. This example illustrates the following rule. When you add a constant to all of the values in a data set, you also add a constant to the mean and median of that data set. On the Advanced Placement Statistics exam, you will also be expected to know what happens to the mean and median when you multiply every element in the data set by a constant. Here's what happens. The mean and the median are also multiplied by the same constant. Again, we can illustrate this with an example using the same data set that we just worked with. In this case, though, we multiply every element in the original data set by the constant 10, which results in a new data set consisting of the elements 0, 20, 40, 40, and 50. To compute the mean of the new data set, we need to compute sigma x, which is the sum of all the values in the data set. Sigma x is 0 plus 20 plus 40 plus 40 plus 50, which equals 150. The new data set still has 5 values, so n is equal to 5. The mean of the new data set is sigma x divided by n, which is 150 divided by 5, or 30. And finally, we observe that the median of the new data set is its middle value, which is 40. Note what we've done with this example. We've multiplied each element in the original data set by a constant 10. And what has been the effect? The new mean is equal to the old mean times the constant 10. And the new median is equal to the old median times the constant 10. This example illustrates the following rule. When you multiply all of the values in a dataset by a constant, you also multiply the mean and median of that dataset by the same constant. Let's review. Measures of central tendency represent the most typical value in a set of values. We described two measures of central tendency, the median and the mean. To find the median, we arrange values from smallest to largest. The median is the middle value. The mean is the sum of values divided by the number of values. The formula for the population mean can be expressed compactly as mu equals sigma x divided by n. The median is the better measure of central tendency when the data set is small and has one or more outliers. The mean is the better measure in large data sets that don't have outliers. Adding a constant to every value in the data set adds a constant to the mean and the median of the data set. And multiplying every value by a constant multiplies the mean and median of the data set by a constant.
That's all, folks.